Again, lecture. We're going to have an exam next week, so next Thursday, a week from today. Tuesday next week, I'll give you a little bit of a, I don't know, a pep talk or something, and try to clue you in on how best to study. Hopefully, you've already figured that out. I understand that there was an observatory session. And just to reinforce, the observatory sessions are great, and I encourage everyone to go every single time that they can. And every single time that they can go, you get 10 bonus points. If you do the observation handout, they have handouts for everybody, and you record your observations, you know, what you see. Did they use the big telescope last night? Yeah. What did they look at? Orion, the Orion Nebula? Excellent, good. So we're going to be talking about that probably Tuesday, actually. So that's good, good timing. Anyways, the thing about the observatory session is, Novell, that it depends on the weather. If the weather doesn't cooperate, then everybody's SOL. But if it's good, I was surprised. I thought, oh man, all those clouds and stuff, they're going to be SOL, but I guess it went. So hopefully it'll go next week, and we've had a good run this semester, and I'm really happy about that. Now, what we're going to do here right now is collect your graphing homework, and then we'll start studying HR. Go ahead and bring your homework. Don't bring your homework up yet. You guys in this section over by the wall, you guys bring your homework up. And just pile it up here on the table. And for the rest of you, get your clickers ready to click. Just slap it there. Very nice. I see a lot of green 12 188s. I see dots. Very nice. Good. Okay. Thank you. Make sure your name is on it. If I don't have a name on it, how can I? What's that? That's good. Yeah, you're good. This is my only astronomy class, so it's not like. Okay, you guys in this section over here. Come and see here. Good.
I spilled coffee on that.
Dude, that no, you just spilled coffee on.
I literally just.
Dude, we got to air this out. But coffee spilled on physics papers is righteous.
Okay. So
it is normal. It's 100%. Yeah, I'll read it.
Okay.
But we got to let it dry out over here. I'll put it over here.
All right. Thank you.
So yeah, that's highly scientific. Spilling your coffee like that. Very good. Thank you. Brandon, could you come on up here in the front? Thanks. All right, how are we looking there? All right, bring your homework. Pencil? Pencil? You want a pencil? Okay, you guys in this section here. Thank you, that's right here. You gotta put your, don't forget to put your name on it. All right, good. Thanks, man. Good. Excellent. Good, good, good. All right. Excellent. Nice. Okay.
Okay, so
Turn in your paper.
I just did it, like, earlier in the library with him and my two friends, and I dropped it. You think it's in the library?
Probably.
I don't know where it is now. Can I redo it and turn it at the end of
No.
class, or can I go find it?
Go find it in the library.
I
Yeah.
don't know if it's there for sure, though.
We'll go look.
Okay.
Okay. Sherlock Holmes times. You'll catch the lecture on YouTube. You got to have that paper. Go find it. All right, you guys in this far side, come on up. Bring your papers. All right. Did you graph it up on the computer too?
Yes, in fact, I actually started that way.
Yeah, I know. That's why I'm asking, because I thought that's actually a good strategy. Did you figure out how to do the vertical scale? Yeah, because it's backwards.
I had a lot of trouble doing it with my computer program.
Yeah, you know, did you
That's what
use
I-
Excel or?
I did use Excel at first, then I exported it to a CSV file, and I wrote my own computer program to read that file.
Yeah, okay. Yeah. Because I think there's a way to do it in Excel. I don't know. I don't use Excel a lot, but a lot of graphing programs will ask you if you want to, go backwards, and you can do it. If you know how, I do it like every couple years that I have to do something like that. So
I just forgot to
yeah, go. All right, you guys got your homework? Yeah, good. Okay. Good. What a semester, man. Yeah.
I got a sling too. I just
All right. Did you turn in your thing here?
Yeah.
All right. That's good. Good. All right. Yeah, just get that in a good, neat stack, please. Thank you. All right. Let's continue with lecture. And, I eyeballed some of your HR diagrams, and some of them look pretty good. But actually, I saw a few that were actually incorrect. So I'll grade them hopefully over the weekend. And if Brandon can handle this task, and then get them back to you next week. We're going to use these on exam 3. It's going to be your personal HR diagram, your personal tool for analyzing data. So you'll actually be using it the way an astronomer would, hopefully. Okay, so if you just got here late, you can turn in your homework at the end of class. We'll probably be dismissing a little early today, so that'll be nice. Now, I want to go and dig into the guts of the HR diagram with you. And to do that, we have to go to the guys that figured out what the meaning of the H&R diagram or the HR diagram is. And that's the guys out at these labs like Lawrence Livermore, where they design hydrogen fusion devices, otherwise known as H-bombs. That's what they do. And so on their weekend for their hobby, they model stars, because a star operates on the same fusion reaction that they design into an H-bomb. And so what they do is, here's another picture. This is actually an important facility for us, the National Ignition Facility. Those are the guys that hope to get a working fusion reactor. If they can get that going, we're going to see ultra cheap energy, especially electrical energy, because a fusion reactor will run on water, basically, on the hydrogen and water, which is basically unlimited. It's extremely efficient. It'll be nice, but it's very hard to do. Anyways, the way that these guys do it, they take a spherical distribution of hydrogen, and then they say, all right, they tell the computer program, let's start with a central pressure of, some extremely high central pressure. at the very middle of the star. And then they say, all right, and then my temperature and pressure at the outer surface of the star, in other words, the photosphere, then they set that. And they figure out if it's consistent basically with E equals mc squared. And there's a huge amount of physics in it. It's very, matter of fact, probably a lot of it is top secret, but that's what they do. And they model the fusion reaction. And what they find is this. This is the HR diagram. And most of you, I'm guessing, saw this kind of diagonal series of stars, Polaris being up here, Sirius and Vega being up here, and then Barnard star being down here in the lower right, and Alpha Centauri and the sun being right here in the middle. That is called the main sequence of the HR diagram. And what we have found by analyzing simply the spectral type and the absolute magnitude, in other words, the luminosity, we have found that almost all stars fit onto this main sequence. And the guys at Lawrence Livermore and Los Alamos and their opposite numbers over in the Soviet Union figured out, yeah, this means that everything on that sequence has the exact conditions we would predict based on nuclear fusion, a hydrogen reaction in the core. You know, and these stars up here, we know from analyzing, you know, Kepler's third law, we know the mass of a bunch of these up here. And these red ones, we know a bunch of these. We know the mass of these down here. We know their surface temperature. So we can simulate the conditions of a stable nuclear fusion reaction in the center of these stars really well. And when you do that, you map out all their total luminosity and the pressures and everything like that from the core all the way out to the surface, and then graph the luminosity and the color, you get this main sequence. So another way to say it is that stars burning hydrogen in the core will have surface temperature conditions and that correlate in this manner to the overall luminosity. In other words, here's another way to say it. If you have a hydrogen fusion system, your main sequence doesn't go from the lower left to the upper right. No, it doesn't. That wouldn't be consistent with E equals mc squared. The trend that is consistent with E equals mc squared and all the nuclear physics concepts is this one. From the hot blue big stars up here to the teeny little red stars down here. That's consistent with E equals mc squared. All right, and we know that now. You know, Hertzsprung and Russell that invented the HR diagram, they didn't know anything about nuclear fusion. Nobody knew about nuclear fusion in those days. But after World War II, you know, first they developed the atomic bomb at Los Alamos and Oak Ridge and Hanford, Washington, based on nuclear fission with uranium and plutonium. And then from that, they developed the fusion reaction devices, the H-bomb, the hydrogen bomb, and that's when we figured this out. So post-World War II. So in other words, for the last 60-something years, almost 70 years. So here's another diagram. Go ahead and make a note. Figure 1210. There's and your homework assignment over the week. You're going to have a lot of homework this weekend, by the way. Well, it's not a lot of homework, but it's 2 homeworks in masteringastronomy.com. And I want you to really read chapter 12. Really read it, including figure 1210. Luminosity and temperature, luminosity and color, luminosity and spectral types. And this graph here, notice that this luminosity goes up in powers of 10. So that makes this a logarithmic chart on this axis. And then the same thing here, it's not, I think this is logarithmic on the, in terms of temperature. So the O's and the B's and the A's are not evenly distributed on this version of color luminosity the way we did for the homework. Okay, so as I've mentioned before, there's a lot of different ways to graph up color on the horizontal and luminosity on the vertical. So let's ask some questions of the main sequence and the HR diagram. Get your clickers ready. And let me ask you a couple questions. And actually, these questions should really function for you as notes. So take notes on the question itself as well as answering the question. Here we go. You have 1 square meter of the surface of a red M-type star and a square meter of the surface of a blue O-type star. Which square meter, so go ahead and write that down, and then the question, which square meter produces more energy per second? And let me start the question. Yeah, that would help. All right, you can start answering. And definitely jot this down as notes because it's significant for us. So in other words, square meter for square meter, which one puts out more energy? The blue O-type or the red M-type star? Or are they equal? Okay, 15 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see. Yeah, we have a distribution of answers here. Some of you voted for M class, some of you voted for O class, some voted for equal. Okay, equal is out. And the concept is that the O class, which 76% of you voted for, yeah, that's the one. Now, why is that? That's our next question. Okay. In regard to the preceding question, what is the decisive factor in favor of the O class? Why does it produce more per square meter per second than the M class star? Right, so make this part of your notes for this, part 2 of your notes for today. What's the critical factor here? Is it temperature, composition, distance, radius? What's the... Fifteen seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for. Yeah, temperature is the correct answer for this, and I see that most of you voted for that. A few of you voted for the others. If you voted for B, C, or D, make a note that the physical factor that controls who has more energy per square meter per second, M or O, the physical factor is temperature, and an informal way of understanding that is judging a hot stove. You observe a stove element that's turned red. You're looking at its color, and you know, okay, don't touch that, right? And so basically, what you're looking at is it's not really a spectral type, but you're looking at the color and judging the temperature from that. And you know that if you put it all the way down to low or simmer, you can probably put your hand on it, the electric element, and it'll feel warm. It might feel hot, but it won't burn you the way when it's up on high and you get total red elements on your stove. So yeah, so temperature's the deal here, all right? And the concept is this: every square meter of a red star surface has the same luminosity owing to something called Stefan-Boltzmann law. And so the joules per second for every square meter is controlled by this formula. This is the Stefan-Boltzmann law. And actually it applies to all star surfaces, not just to red stars. In other words, the joules per second, don't forget, this is a watt. So watts per square meter, that tells you the luminosity or the luminosity density of a source. And the solar constant, we know that that's about 1,367 watts per square meter at Earth, and a little bit less than that at Mars and so forth. So yeah, if you think about, how, 1 square meter of a red star surface, the number of joules of energy it produces per second is controlled by the temperature. Now, sigma here is a constant, right? It's called the Stefan-Boltzmann constant. Go ahead and write it down. And it's 5.67 in the metric system times 10 to the minus 8 watts per square meter per Kelvin to the 4th. So if you multiply sigma times the 4th power of a temperature on the Kelvin scale, so like for the surface of the sun, it's 5,800 kelvins, quantity to the 4th power, which is a big number, and then multiply that by sigma, then you'll know how many watts per square meter burn off the very surface of the sun. And this is also true for most objects. So you have a surface temperature, 98.6 Fahrenheit, which is 200 and, I think it's 310 Kelvin, 290, somewhere around 290, 300, 310. I don't have that memorized, but it's up in that area. And so you have a sigma T to the 4th number of watts per square meter burning off every square meter, and then multiply it by divide by 1,000,000, and you'll have the number of watts per square centimeter burning off the surface of your skin. And a lot of it is infrared, which is why you can't turn yourself off at night to someone that has night vision goggles unless you're like inside of like a cold, chilled suit. It takes the surface temperature of the environment and totally reflects all your body heat back inside the suit. But you couldn't really walk through the forest that way. You couldn't sneak up on anybody that way in a suit like that. But yeah, I mean, you put out a lot of infrared. Everything puts out infrared or ultraviolet if it's really hot, according to this law. All right, next question. How do you interpret? And so now we're trying to think, and this is number 3. Actually, this is number 4 for your notes. Stefan-Boltzmann formula was number 3 for your notes. Here's number 4. How do you interpret a star in the upper right of the HR diagram? Okay, upper right, that's up here. So it's on the red end of the HR diagram. It's over on the right. It's an M spectral type. But it's very luminous. It's near the top, right? So it's off the main sequence. It's off this. It might not be burning fusion. It might not be fusing hydrogen up here, but we know it's, I mean, and we see stars. Matter of fact, Betelgeuse, in the data that you plotted, Betelgeuse is up here somewhere, all right? Off the main sequence diagonal and over to the right and very near the top. So, question. How do you interpret that? Go ahead and vote. And make sure to jot this down as your notes, if you please. "15 seconds. Five, 4, 3, 2, 1, 0. Okay. Let's see what we got here. Let's see what you guys are thinking. Ooh. We got some splaining to do. All right. No, that's good. You know, you're being graded for participation, and this is a difficult analytical decision. Now, I've given you 4 options, but it's not easy to figure out to analyze this kind of stuff. So let's talk about it. The surface temperature is hotter than other M-type stars. No, that's not right. It's the same color. So make a note. Option A is wrong because every square meter of an M-type star produces the same amount of energy per second, right? So A is out for that reason. If you know the color, you know how many joules of energy per second are burning off every square meter or every square centimeter or every square nanometer of your object. Option B, there's a lot more hydrogen in its core than a star on the main sequence. Well, that may or may not be true. You cannot tell that from this diagram. And in general, that is not a lot. C, its diameter is larger than the main sequence M-type stars. Now, the main sequence M-type stars down here, they're pretty dim. Now, they've got the same amount of energy per second, Sarah, coming off every square meter down here. Same thing up here, but this one puts out a lot more. So your answer here is you've got a lot more square meters up here. All right, so make that your addition to option C, which is the correct option. All right, option C is correct. And so if you made that deduction, 34% of you did that. That's great. All right, and now you know the reason that is the correct. And so in general, as I've mentioned to you, if you can get parallax and get a distance, that lets you map a star on the vertical scale. If you can put its starlight through a diffraction grating and figure out its spectral type, that tells you, did you find it? Did you find it? Okay. If you put the starlight through a diffraction grating, you can figure out where it is on the spectral type scale. And then that'll tell you where it is on here. And what you can deduce from that is the relative size of any star in the HR diagram. All right? And so this upper corner, here's another HR diagram. The main sequence on this diagram, this one's in terms of the luminosity of the sun and the surface temperature down here. Okay, so this is not spectral type. down here on the horizontal, but they're equivalent. And here's your M's over here, and here's your main sequence, this kind of blue line, all the way up through here. And here's where Betelgeuse is up here. It's not graphed up on this HR diagram, but Betelgeuse, those are the really big ones. They have about 1,000 times the radius of the sun, all right? And so Betelgeuse would, you know, take up most of the inner solar system. It's, I believe I made a note of this a couple weeks ago, that its radius would extend out past the orbit of Jupiter, I think, is how that would go. It's pretty big. So mapping out based on surface temperature or spectral type horizontally, parallax getting you absolute magnitude or luminosity vertically, you can figure out the size of a star. It's pretty sweet. And the guys at Lawrence Livermore verify this. They know, yeah, if you do this, the main sequence is going to have a sequence of sizes from about 10 times the radius of the sun down to about maybe half the radius of the sun. All right, so that's most of the main sequence. There's going to be bigger ones. There's going to be smaller ones. But then there's going to be stars. We know this from charting it out like Betelgeuse. They are out of the pattern. What does that mean? Well, one of the things that it means is that they're bigger. Down here, Sirius B, you had, I think you actually had 2 stars down here to graph up. You remember that? And you had one down here kind of sitting out here. If I'd given you 1,000 stars, you know, 1,000 nearest stars, you'd have had a few more down here. Those are called the white dwarfs. They're called white because they're the same color as Sirius. You know, they're blue, but they're pretty tiny. They're not very luminous. So this is the opposite. This is the opposite of Betelgeuse. Betelgeuse has a cool surface. It's red. It's not very hot. But it's got a big, huge surface, so it pours out a lot of light. All right? Opposite to that, white dwarfs, yeah, they're burning off a lot. Every square meter of a white dwarf is burning off a lot of energy. It just doesn't have many square meters of surface, that's all. And the white dwarf down here is roughly the size of Earth. So these are Earth-sized objects down in here, all right? You know, plus or minus a few hundred, plus or minus a few thousand kilometers. All right, here's some more that I want you to look at and analyze and really study figure 1216 as well. This is the one that we just looked at. I believe this is in your book. Here's Betelgeuse up here. These are called the red giants up here, by the way. So remember when we talked about the Stardust mission and they said, yeah, that one little bullet hole, we found that little pre-solar grain, a little speck, and it was from a red giant star? Yeah, this is the kind of star they were talking about. And believe it or not, these red giant stars are near the end of their life. And they're going to go, many of them will go into a supernova explosion if they're big enough. And these ones up here are blue giants, okay? And Vega and Sirius, they're over here. They're on the main sequence. But these guys up here are considered blue giants. And there's all kinds of subgroups and stuff like that. Main sequence down here. And then the white dwarfs, they don't really have it on this chart, but the white dwarfs would be down here to the lower left. And it's the HR diagram is it's like the kitchen sink for an astronomer. I mean, you can get everything. You know how you know, okay, I'm going to try everything I'm going to throw in the kitchen sink. You know, that's a saying. Well, this is like kind of like the kitchen sink. In other words, by analyzing a star and its location on the HR diagram, you can extract an enormous amount of information about that star, as long as you know a little bit of E equals mc squared and a little bit of nuclear physics, okay, which we're not going to learn in this class, but here's figure 1211. All right, so let's just finish with a couple points about this. The main sequence stars, they are fusing hydrogen into helium. Now, the red giant stars are not. A red giant star might be burning or fusing helium into stuff further out on the periodic table, like carbon or nitrogen or oxygen. Okay, so the luminous blue main sequence stars are hot, they're blue. The medium ones are cooler, either yellow or red. And the sun is, as I mentioned, yeah, the sun is G2, absolute magnitude 4.8 approximately. And so it's right down here in the middle. And my wonderful students, there are zillions and zillions and zillions of stars just like the sun. So we think of ourselves as being pretty unique in the universe. But in terms of stars, the sun is not that unique. There's zillions of them. We're unique as far as we can tell. Nobody's ever been contacted, but somebody up here in the fourth row just gave me the eyeball like, yeah, space aliens exist or something like that. Anyways, we've never been contacted. So far as we know, we're the only sentient beings, except for Hollywood. I mean, Hollywood's all about, Decepticons and stuff like that. But so far as we know, we're unique as sentient beings. But star-wise, very common. And so the binaries, if you could find some binary stars on the main sequence, boy, you can get everything. You can figure out their overall lifetime, how long they're going to live, because you have their mass, and you can figure out, are they going to become a supernova? Are they going to become a white dwarf at the end of their lifetime? Or are they going to become something even more exotic, like a black hole? What is going to happen? Are they going to become a neutron star? If we can get a pair of binary stars on the main sequence, we're in hog heaven, and they've gotten buku of them. So we have a pretty good idea of basically what's happening in any galaxy that we can see. We trust that it's going to be a lot like our galaxy, because we've seen big numbers of stars in our galaxy. All right, let's dismiss early today. You have 2 homework assignments running in masteringastronomy.com on the HR diagram. You're dismissed. I'll see you on Tuesday.